Hello, this video will be to explain problem number 19 in chapter 3. Starts off by explaining you're basically aiming a hose at an unspecified angle. So here's the hose, it's got water coming out, and you'll have an angle here relative to the ground. It should be obvious that the water is going to be uh, traveling in a parabolic arch because it's going to go up for a while, and then because it's being pulled down by gravity, it's going to arch like this. Okay. Now, here, this angle we will call theta. That's what we're looking for. And we're told that the velocity initially coming out of the hose is of the water coming out of the hose is 6.8 meters per second. And I'm going to state that the initial position is 0 meters. And they specify that the final position, the distance that the uh, water travels horizontally, is 2 meters. So x final will be 2 meters. Now, this is a range problem. We have an angle that we're looking for. We have an initial velocity. We know the distance it's traveling. And we know that the acceleration is g, which is 9.8 meters per second squared, downwards towards, um, so g goes down. So with the range equation, you use the value of g, the magnitude 9.8 meters per second squared. You don't use a negative value for g in the range equation. So what I would do in this case is say down is positive and to the right is positive. That means g is positive and this initial velocity is negative because of that upward um, velocity. And the position here is positive. Now, there's one thing that's important to realize. The problem tells you there's two angles, so that's uh, at least given to you as a known. You know you're looking for two, but it's important to know why you're looking for two. So to help you understand that, I'm going to draw a second smaller diagram on this right side. Let's go with gray. Now, the hose is only being pointed in one direction, so the the water has to travel within this quadrant I just drew. Now let's say you had it at 45 degrees. At 45 degrees, it should have the longest range possible. Because the horizontal velocity is going to be equal to the vertical velocity. Those two would equal. Okay? But if you have an angle, let's say it's 30 degrees. At 30 degrees, the, let's see, try to change this. At 30 degrees, the velocity in the x direction is larger than the velocity in the y direction. So I try to show that graphically where Vx is significantly larger than Vy by just showing the size there. Okay. However, I'll do a different shade of green. If you did 60 degrees, Vy would be significantly larger than Vx. The reason for this, or this actually is the reason for the water traveling at this to the same range for 30 and 60 degrees. The horizontal velocity of this first green line, the lighter one, makes it so it's traveling further in the x direction for each second, but because the velocity in the y direction is smaller, it doesn't spend as much time in the air. In contrast, when you have it at 60 degrees, the vertical velocity in the y direction is greater, so it takes a longer time period for it to go up and then come back down. Because it takes longer time, the smaller velocity in the x direction can still yield the same displacement as the 30-degree range. So hopefully you guys identified those are complementary angles. So that is the way it works for all of the um, projectile motion problems. You always have this situation of complementary angles. So in the situation that they're giving us, they're saying you have an angle, might be like this, and you're going to end up having to find the complements. You have to find theta 1 and theta 2. Oh, 2. So over here, back at the original problem, we're going to need to change it so we have a theta 1 and theta 2, and we don't know what those are. However, we do know that theta 2 will equal 90 degrees minus theta 1. Okay, so if we just find theta 1, we can easily find theta 2. Let's see, we have all of our values in the correct units. We have the correct signs on our vectors. So you basically just need to identify the equation. I've already told you it's the range equation. So the range equation is delta x equals the initial velocity squared times the sine of 2 theta. Now this is going to be theta 1, but the equation is always theta over g. So let's go ahead and rewrite it for our specific problem. So the range equals v initial squared sine of 2 theta 1 over g. Now we need to isolate, so we'll end up multiplying by g, dividing by the velocity squared, and taking the inverse of sine. So let's do everything except for the sine part for now. So when you do move over g, you get delta x times g, then you divide by the initial velocity squared. That would all equal sine of 2 theta 1. Then you can take the inverse sine, so you'd have 2 theta 1 equals the inverse sine of delta x g over v initial squared. So if we plug in the values and we divide by 2, we'll get the sine, I'm sorry, if we take the values on the right, divide by 2, we'll get theta 1. So we'd have 2 theta 1, we have theta 1 equals inverse sine delta x multiplied by g v initial squared, and all of that divided by 2. Plugging in our values, we get theta 1 equals, now delta x, that's just your change in positions, that was just a positive 2 meters, and g was a positive 9.8 meters per second squared. The initial velocity was a negative 6.8 meters per second, and all that was squared. And then you have to divide all of that by 2. You should get a value of theta 1 equals 25 point, no, I'm sorry, not 25, that's before I did the 2, 12. You should get a value of 12.54 degrees. When you look at the sig figs, you only need 2 sig figs, so that'd be 13 degrees. Now this is one of the cases where you actually do not use the unrounded number to find the second part, because as we said in the colored diagram to the top, you have to have the two angles add to 90. So we're going to use this rounded number to find theta 2 so that they add to 90 degrees. So we'll go ahead and do that over on the left. So we had theta 2 equals 90 degrees. Now we subtract 13 degrees, so you get theta 2 equals 77 degrees. And then you box that. Okay, because again, you need to please box your answers. Makes it easier to identify where your work ends, especially on your test. So you should be boxing your answers. Now for the sentence on this, you would explain that the hose could be at 13 degrees or 77 degrees. It's a reasonable answer because you know that there has to be two angles that are complementary to each other that would yield the same range. If the angles were not complementary, then they wouldn't yield the same range because the ratio of the horizontal velocity and the vertical velocity would not equal. Okay, because that's all this is dealing with ratios. So that's basically the explanation that you need once you found your answer. If you do not understand this conceptually, you definitely need to go back to your book and do some reading. This will not just be in theme in kinematics. You're going to be using this understanding going forward. And on the AP test, it will be referred to again. You need to know this and understand this in the kinematics section because it's a very common question to ask to make sure you really understand what's going on. But the ratios of the horizontal velocities to the vertical velocities need to be understood. If I went too fast on that, you could always rewatch the video, or if you need a different method of understanding it, you look at the book. They have a whole section of it. Just look for the same diagram that I just drew in the book and take a look at that.